So in this video, I'm going to spend some time just walking through some of the problems with you, so you at least have some idea of what I'm looking for. So the intent of the video is just not to provide a bunch of answers, but hopefully address most of the questions that you might have asked about us in class today. So in problem number one, what they're asking you to do is figure out the area of this rectangle here based on the information that's given. I would be looking for numbers that, like lengths that you're already given, like such as the 7 or the 8, or the 10, 15. Try to use those numbers to see if you can figure out some of the other missing numbers. And with the idea of trying to figure out what the length and the height is of that rectangle in the bottom corner. I would suggest anytime I'm saying to you, discuss your answers with at least one or two classmates. Go ahead and do that. And if I ask you to explain how you would come up with an answer for something to somebody's absent, try to be as thorough as possible, but try to let the picture also help support whatever it is you're trying to say. At the bottom of this page, this is actually something we've already done more than once in class. We've done at least 4 of these, 3 or 4 of these at this point. But if you don't remember the rule in terms of the area relationship, go back to It's Learning. I posted the sketch in today's activities, and go back and kind of move those pieces around and see what the relationship is. I'm not really focused a lot on length, but I do want to talk a little bit about length as we work through this. So if the area of a square happens to be 6, the length of that side is the square root of 6. Pythagoras, who actually created the idea of a square root in terms of the number system, chose a square as the shape to put off the side of the triangle because he understood that every square has a unique area. In other words, there's only one square with an area of 4, that's a 2 by 2 square. There's only one square with an area of 9, that's a 3 by 3 square. There's only one square with an area of 6, and that's a square root of 6 by square root of 6 squared. So if I have a square area, let's say, of 225, that means the length of that is the square root of 225. And sometimes those square roots do simplify to a whole number, and the square root of 225 is 15. So always be willing to check the square root length to see if it actually can simplify. But kind of starting point for length is the square root. It's the square's root actually means length. It's the square's length using its area, because every square has a unique area. So this problem here, what I'm asking is for you to take a ruler and to see if you can come up with a drawing that using 4 lines in all of them that will give you the correct number of points of intersection. So the first one, 4 lines of no points of intersection. This one has 1 point of intersection. So if all 4 lines are meeting in one place. 2 points, 3, 4, and 5. And then I'm asking you, can you actually come up with the maximum? Can you think about if I was going to draw a bunch of lines and they were intersecting each other, how could I guarantee figure out the maximum number of points that are possible when drawing 4 lines? If any of the lines happen to be parallel, if a parallel sketch is helpful in being able to get that number of points, make sure you use parallel lines symbol, the arrowheads. You may find some of these are just not possible, and so if it's not possible, I don't believe it's possible. And then we'll leave the discussion for why it's not possible when we meet on Tuesday next week. This activity is a continuation of the activity that I asked you to do on Wednesday. And this is the Venn diagram using David Hilbert's definition for trapezoid and kite. So a quadrilateral, by David Hilbert's definition, is a trapezoid is a quadrilateral that has one set of parallel sides. Because it's not saying only one set, that means that parallelograms, rectangles, rhombi, and squares are all trapezoids. So hopefully when you drew this, you put all those shapes, parallelogram, rectangle, rhombus, and squares inside the trapezoid loop, because by taking away the word only out of the definition, all those shapes have one set of parallel sides. I also added in the kite, so the original activity didn't ask you to do a loop for the kite, but I asked you in this one to do the loop. David Hilbert removed the word distinct. He basically says a kite is a quadrilateral with two adjacent sets of congruent sides. Those two sets, under Euclid's definition, they're distinct, which means the two sets have to be different lengths. Under David Hilbert's definition, that word's removed, which means the two sets can actually be the same length. So in terms of the video, the blue loop here is the kites, and that kite loop includes squares and rhombi, because rhombuses and squares do have two sets of equal sides. Because it doesn't matter what two sets I choose, because they're all four sides of the same length. So there's different definitions for these shapes depending on who writes the book. So we are using for your textbook the only one set for trapezoid, distinct sets of congruent sides for the kite. But I also want to spend some time talking about the fact that mathematicians have explored different definitions and different ways of grouping these shapes, and they're all right based on the definition or rules that they're using. The main part of this activity is mapping. So another activity I asked you to complete on Wednesday involved I think it was a square, and the square was divided up in a bunch of pieces, and you were supposed to go through, and you had 4 color choices, and you're supposed to go through and decide if there's a way of placing colors in each side of those pieces so that no two pieces that were adjacent to each other or next to each other shared the same color. So no two red pieces can share the same edge. They can share a vertex, that's fine, but they can't share a side or an edge. So we're going to continue with what's called the 4-color map problem. It's an old problem that map designers knew 4 colors worked, but they could just never prove it. So there's a video in your Instagram account that kind of goes into some greater detail about the 4-color map problem. Make sure you watch the video so you at least have an understanding of the work that was done to come to that final answer of why it works. And what we're going to do as you work through these are on, I think these are 3 colors here, and then this one here is 4 colors. So as you're working through these problems, the main activity is going to be this 2-color theorem. So a theorem is an idea of a proof, some way of trying to prove something so that we know it's always going to work. And so the goal here is, can you figure out for any design whether or not I can actually shade in the entire space just using 2 colors, and no 2 pieces that are next to each other in terms of shared edge are going to have the same color. They can share a point, a vertex, but they can't share an edge. So for example, this piece down here and this piece right here, they're only sharing the point right here where my cursor is. So these 2 pieces here can be the same color, but these 2 pieces here cannot, because they're sharing this edge. These 2 pieces here can be the same color because all they're sharing is that point. But these 2 pieces here cannot be the same color because they're sharing this edge. So you're looking at, if they share just a vertex or a point, that's good. They can be the same color. But if they share an edge, no matter how small it is, they have to be different colors. So I'm starting off with problems involving problems that involve a almost perfect design. And so I'm asking for you in here to do is, can you figure out how to finish this problem off? Because currently, this problem can't be done with just two colors. And it's saying in here that we need to add a line to be able to finish it off. And so each of these problems you're going to be looking at, they have an error somewhere. And because based on the design, you just can't put two colors next to each other without somewhere along the line the two colors being the same. Can you figure out where that's occurring in these designs? And can you figure out a pattern or what we call a theorem, a rule, that will be able to allow us to identify which ones will perfectly work for two colors and which ones do we have to fix? So we have, there are two problems here, and then there's two additional problems here. And then I'm asking for a rule. A map is a two-color map if. Can you tell me what's happening here that kind of guarantees that these two colors will always work? But we will discuss this activity on Tuesday of next, or yes, Tuesday of next week. So if you don't get it finished during class today, please complete the problem outside class. There are also two additional problems, 1920, and both these problems come from the homework assignment from lesson 2-1. So bring back your questions on Monday, or I'm sorry, Tuesday when we meet. But again, do your best to complete the activity for our next class period.